So this is the talk that wasn't on the schedule until this morning when Mike, my boss, very kindly volunteered me. Testing as an equal first-class citizen to coding, and I'll explain what I mean by that as we go through. So this is me. I, like Mike, work for Merkely. Before I worked for Merkely, I was a self-employed person in various disguises for 20 years, and I was lured by Merkely because it's just such a fantastic opportunity. And I know everyone says we're hiring when they're up the front here, whether they are or not, but we are. So if you're interested in some of the stuff that you hear me talk about, or that you hear Mike talk about in the opening talk, feel free to come and see us. We'd love to chat. So I'm throwing out some chocolates now, virtual chocolates. Yeah? And I'd like to talk about what happens when you eat chocolate. You'll see why in a minute. So when you eat a chocolate, the glucose gets into your bloodstream, which causes a spike in the glucose. But very rapidly it gets into some kind of regulation. It goes down, but then it comes back up and down and up and down and up. But as you can see, it stabilizes at a certain point, pretty rapidly, in fact, which is a good thing. Because when it doesn't do this, bad things happen. So let's look at this in more detail. Is there a pointer thing in this mic?
Yeah, if you hold down the spot and point it at the screen.
Oh, yeah. So this is a glucose molecule here in the middle. And when you eat sugar-rich foods, your glucose level goes up. And if it goes up unchecked, this is very bad, and you get hypoglycemia, which we can see at the top here. Now that doesn't happen in a healthy mammal, any mammal, because there's some cells in the pancreas that detect the increase in glucose. That's their trigger to secrete insulin. The liver and the muscles detect the insulin, and that's their trigger to grab the glucose and put it in a stored form called glycogen, which has the natural effect of reducing the amount of glucose in the bloodstream. And so you don't get this unchecked spike of glucose causing hypoglycemia, and you don't die. But if this happens unchecked, then the amount of glucose is too low, and it keeps getting less and less and less, and you die from technically hypoglycemia rather than hyperglycemia. Well, who cares? But again, that doesn't happen for a very similar reason in a healthy mammalian body. I don't know why I'm doing this. I'm not particularly healthy, but I am a mammal. Okay? There's some different cells in the pancreas that detect this happening. That's their trigger to secrete a different molecule called glucagon. The liver and muscles detect that one, and that's their trigger to reverse the earlier process which stored the glucose in the glycogen, and they put the glycogen back into the bloodstream as the glucose, which has the natural effect of increasing the amount of glucose in the bloodstream. I find this deeply beautiful and deeply paradoxical for reasons we'll talk about in a minute. But I'd just like to point out to you here that there's two cycles of activity. There's kind of the top one that you can see, and there's the bottom one as well. And these are fighting against each other. You can't see it, of course. It's all inside the cell. But there's this tremendous activity. That's the point I'd like to get across here. There's all of this activity. Lots of activity, lots of activity. All of this activity. Going and going and going. Fighting against each other. Fighting. Activity and fighting. Activity and fighting. Why? Why all this activity? To keep something else the same. That's the paradox that I see and love. And this has a name. It's got a couple of names, actually. It's ubiquitous across biological systems. That's just one tiny example. The fancy name you might see if you look it up on Wikipedia is Le Chatelet's law, after a French gentleman whose surname was Le Chatelet, who was the first person to probably not discover this, but to at least document it in a way that got him noticed, and so his name was attached to it. More colloquially, it's called the equilibrium law. And my I stole this summary of the equilibrium law from a book called The Systems Bible by John Gall, which I highly recommend if you're into systems thinking, this idea that we're very briefly touching on as an example when we think about these two systems fighting against each other. So John Gall says, stable systems tend to oppose their own proper function. And I didn't really get this when I was younger. And looking back, I think it was partly because of the words oppose and proper. Why would you oppose the proper function? You don't want to oppose the proper function. It's the proper function. Just leave it alone. Didn't really get it, and I get it now, I think, much more clearly. And it is, again, this opposition of these two systems to each other, which is what creates the stability, the equilibrium law. And another reason I think I didn't get it when I was younger was because I have a natural bias to thinking about things statically rather than dynamically. I don't know whether that's a common bias. I suspect it may be. To give you an example, in the background here we've got some bird of prey, a hawk maybe, rather brutally eating a rabbit. Let's say, I think it's a rabbit there. Well, it might be another little bird, I can't see, it doesn't matter. Let's say it's a rabbit. And the point is that eagles, hawks, whatever it might be, regulate the number of rabbits, fairly obviously. But the rabbits return the favor. Yeah, there's a natural cycle of these two things. Thinking dynamically rather than statically. Wouldn't have got that when I was younger. Now I get it. And I can see things much more richly. It gives me a richer experience. And I'd urge you to try and think about this. If, like me, you feel, now I put that idea in your head, that you have a bias towards this thinking statically. So as Charles Darwin might have said, but did not, as far as I know, evolution is always co-evolution. Things are always evolving in opposition to each other, in a web of dynamic interactions that we can't see often. But that is, all of that activity is what is creating stability at other levels. So a quote from one of my favorite books, The Aesthetics of Change, which isn't perhaps what it sounds. It's actually a book about family dynamics. And it's a brilliant book by a man called Bradford Keeney, who was a disciple of... Who was he a disciple of? I'm going to see him in a minute. We'll get to his name in a minute. I've forgotten his name. So this is his quote. All change can be understood as the effort to maintain some constancy, and all constancy as maintained through change. I love that quote. So to think about that, and to give you a rule of thumb, a way to think about things that maybe you hadn't thought about, I certainly hadn't, was when you are experiencing something that is the same, maybe using this idea you can think about why it's the same. Most things don't stay the same left to themselves. So if something is staying the same, like we saw the blood sugar level, the glucose level, maybe there is lots and lots of activity going on that you can't necessarily see again, unless you search for it maybe, that's keeping that thing constant. And vice versa. These two things always go hand in hand. It is only when we have some level of constancy as a floor to stand on, if you like, that we create the luxury of the activity above that to create the roof of stability yet again, which becomes the floor of activity at the next level up. This is how one of the ways that structure can actually grow. This has a name, it's called homeostasis. I find it interesting that the name we choose to use for this process of keeping things in regulation isn't named after all the activity, it's named after the stability. Yeah, again, I think that's that bias that tends to come through slightly. So, having planted that idea in your head, I'd like to ask you this question. Don't shout out, anyone. But just think about in your head, if you can for a moment now, what's the answer to that question, or answers to that question, as it's posed on the screen. Try and be conscious of what your thoughts are when that question is posed. Yeah? And if, like me, you have a bias towards static thinking, let's say, you probably answered the same way that I answered this question when my friend asked me this very same question many years ago. I said, duh, to break. Yeah? And he said, yes, that's true, but there's a more useful answer. There's a more constructive answer. Yeah? That answer is that cars have brakes so that you can drive safely. Would you drive a car that doesn't have any brakes? Probably not. Yeah? The faster you go, the more important it is that you have good brakes. It's not an accident, for example, that lorries and Formula One cars have different kinds of braking than regular cars. Yeah? In lorries, it's often induction braking, for example. Yeah? So you might be thinking, why am I talking about all of this at this point? I'd like to introduce the idea of testing as an equal first-class citizen based on this idea, fundamentally based on this idea. Testing and coding opposing each other, those are the two primary levels of activity that create the stability that we're after in the middle. And again, to think about this in a practical way, it's about regulation. When we talked about the glucose levels in the body, it only works if you get the glucose level back to regulation within a certain time frame. Beyond a certain time frame, and sadly it doesn't work, diabetes, for example, is a classic example of that, it has to be within a certain amount of time. So that's the idea of regulation. How much activity are you performing? It costs something to do that, and the benefit you're getting is that you're bringing the system back into regulation within a certain time, which, if you think about it, has, yet again, strong echoes of this idea of measurement that's been a common theme through some of the talks. Measure something so that you can know how quickly you can get it back into regulation is one of the key DORA metrics. Equal rights for tests. This is my grandson, Kobe. He was born a couple of months ago, and I pop him up there just because he's so cute, but also to point out that this biological stability is unbelievably robust. Yeah? Life's been on Earth, by most estimates, for roughly 4.5 billion years. That's roughly when people think it started. Yeah? Which means that he and I, and every single one of you, is the result of an unbroken chain of survivors going back 4.5 billion years. Just blows your mind if you think about it, doesn't it? Or to put it another way, we've been the subject of 4.5 billion years of destructive testing, and we're still here. This is robust. So I think there's a strong tie-in with this DevOps movement, this idea of regulation, this idea of measurement, and learning the lessons that nature has come up by itself, albeit it took 4.5 billion years. We're doing it a little bit quicker, which is just as well. We may need to be very quick quite soon if climate change gets worse. So to base this idea of equal rights for tests, I'd just like to look at 3 very simple questions based on something as humble as the function, just to bring it back to something a little bit more practical, and maybe startle you with some thoughts that you perhaps haven't thought about before. So the first question is, what does a function do? What does it print, as an example? What does a function do? So I'm talking about equal rights for tests here, so I'm really not interested in what regular functions do. I'm interested in what test functions do. What do test functions print? That's the real question. Yeah, what do test functions print? Hands up if you've ever had a failing test that you thought was passing or vice versa. Pretty much everyone's hand's going up, naturally enough, yeah. So I claim a test function should do one thing when it fails and something completely different when it passes. This is different to a normal function. A normal function is designed to do one thing and to do that one thing well. Cohesion is the word we use for that. But tests are different. When we're in a TD cycle, we have this duality of the red and the green, and the refactoring when you're at green, which is very important, but there is this definite difference. So it's a mistake to think that equal rights means equal outcomes. The context matters tremendously. Yeah? In this case, it is literally that there is this 2 states that we need to think about. So, as Gregory Bateson, who's the name of the gentleman I couldn't remember earlier from the Bradford Keeney book, said, what we're looking for is a difference that makes a difference. Isn't that a lovely, pithy phrase? A difference that makes a difference. We don't want to be fooled into thinking that this is a test that's passing when it's not, or vice versa. We want the difference between a passing test and a failing test to be as clear as we can make it. Simple, practical idea. So when a test function fails, you'd like as much helpful diagnostic information as you can get. So looking at words again, thinking statically and dynamically, here's a noun-verb thing. What do we want diagnostics to do? We'd like them to help us diagnose the problem that we're experiencing, assuming this wasn't an expected failure, right? Do test outputs actually help you diagnose the problem? I find a lot of the time, not so much. They really and truly, we could have put a bit more effort somewhere along the line to get more helpful diagnostics. Why didn't we do that? Because we don't treat tests as equal first-class citizens. Even these companies, and more companies do really good testing, much better than they did years ago, because they finally got this idea about a CI/CD automated pipeline. And they've realized that if you're doing 10 deploys a week and you want to do 10 times that number of deploys, unless you increase the quality by the same factor, it's not going to work. But all things being equal, a system will be in balance, like we've just been talking about. If it can handle 10 releases a month, or a week, or whatever it might be, it really can't handle 10 times, a multiple of that. It's stable at that level. Yeah? The quality goes up, the amount of times you can do it goes up. The things are tied together hand in hand, yes? Just a little echo, hoping it makes you think the same way it did for me. This is the kind of thing that you get when a test fails. Just as an example from PyTest. And therefore, when a test passes, you want almost nothing printed to make that difference as clear as you can make it. And I see people not doing this a lot of the time. I see stuff like this. I've sat next to people on more than one occasion. They've been running the unit tests. It happened with Arstan. Do you remember Arstan? One of the early days we were working together, right? And he ran the unit tests, and they were all passing except one. There was one that was failing. You could see it flash by red. They go by green here in the past if it's passed. One of them was red, flashing by. Lots of unit tests. They're flashing by, they're scrolling by. We're waiting and waiting. Because this stuff, just printing to the damn terminal takes too long. If they hadn't been printing this stuff, we'd have got the answer like that, okay? But it's scrolling by. And eventually it stops, and we think, okay, all right, let's scroll back and get the failing test. We're scrolling, and we think, well, this is taking a long time. We pause, and we look at the actual the scroll bar, and it's tiny. We think, well, if we just do it like this, it's going to take forever. So we go to the scroll bar, we click on the scroll bar, and we zip right to the top, and it's gone. Our history was not big enough. We'd lost that test failure. Yeah, and we can't even see, perhaps, the random number that was used to generate this test run, and now we can't reproduce it, right? Because you've relied on this output as a crutch almost to sort of give you some level of confidence, even though it's not really a good idea, as I suggest. Almost nothing if the test passes. That's what I would suggest. Just keep as a minimum, the number of tests, and hold in your head how many tests have run. We've added a new test. There's going to be one more. It's not difficult, okay? Question 2, what is the complexity of a function? E.g. the number of different paths. So here's a function f. We look inside it. We can see there's 3 paths through this function. So we give it a measure of 3. Very simple complexity measure. Not interested. I am interested. But what I'm also interested in is the tests. If we have a measure of the complexity of a function, shouldn't we at least consider using that same tool, a measure of complexity, for the tests? It's a reasonable idea to at least consider that idea. Equal rights for tests. At least consider it. So here's the test for F1, the function we just saw a moment ago. That has 5 paths through it. Can anyone see a problem?
One fails, you don't know which one fails?
The measure of the complexity of the function f was 3. Lower is better. Higher is more complex. The measure of the complexity of the test is 5. You've got less confidence that the test is right than you do than the code it's testing, right? Now, the way not to solve this problem is to create a meta test that tests tests, and that's got a complexity of 26, right? In this case, what do you want? You want this to be reversed. This greater than is in the wrong direction. What we want is this, and if you're not familiar with this operator, this is the much less than operator, okay? We want one. We want one path through each test. You necessarily have more individual tests. That's the way you break that otherwise cycle that would defeat you, right? In other words, the tests become specific. There's an interesting word. What's the first 8 letters of the word specification? Specific, right? Different ways of thinking about the same thing. But most importantly, it's this idea of thinking about the tests as equal first-class citizens. Practically, if you're using a tool for the code, think about using that tool for the tests. Sometimes it doesn't make sense. Sometimes it makes more sense than you think. Sometimes you think it doesn't make sense and you try it anyway and you learn things that are completely unexpected. And the last question, what is the coverage of a function? For example, simple statement coverage. Yeah, so simple setup here. Let's imagine there's f again, our function. 3 tests that test f. Test F1, test F2, test F3, imaginatively called. Yeah. We want to measure coverage, so we instrument, this is an instrument, haha. We instrument the code, the function, f. We run the tests, and we see there's 9 statements, let's say, and 8 of them get covered. There's 1 statement that's not being covered when we run these 3 tests. Okay, fine. Suppose the missing 9th statement can never be covered. You're confident it can never be covered. Should you delete it? Are you confident enough to delete it? Sometimes people are, sometimes they're not. Again, it depends how strongly you embrace this idea of tests as equal first-class citizens. Do you get enough confidence? If you don't get enough confidence, think about that. Right? Because this matters. There was a company called Night Trading in the 1980s, and they did automatic trading on the New York Stock Exchange using C++ as their code base. And they had dead code in their code base, and they didn't remove it. And in C++, when you get undefined behavior, who knows what happens? Absolutely anything. That's why it's called undefined. People sometimes don't quite get that. Undefined behavior means it's undefined what can happen. And on this particular moment, there was a bit of undefined code in their C++ automated trading system. And at that moment in time, it caused the program counter to jump, guess where? Into the dead code. What did that code do? Automatic trading. Very, very fast. Yeah, and it hadn't been run, let alone tested, in years. And they lost over $450 million in less than an hour, and they no longer exist. Right? So computers are great at doing the right thing really, really fast, but they're also really, really good at doing the wrong thing really, really fast. Testing matters. Equal rights for tests. The tests, the code, giving you the stability, the regulation within a certain period of time. So we just looked at coverage for the function. I'm introducing this idea of the coverage for the tests. Now, at this point, sometimes developers think, this is sort of, you can see the brain going, short circuit. They don't immediately get it, and I was the same. I'm not talking about the function f here. We're talking about the tests that test the function f, which we're now ignoring. We're simply instrumenting those tests to see how much coverage they have, right? There's 3 of them. The first one has 14 statements, the second one has 23 statements, the last one has 19 statements. What coverage do you think you're going to get? They're tests. They each have a complexity of 1. They do one thing. What do you think you're going to get? Not a trick question. What do you think you're going to get? Full coverage. That's what I thought. And a lot of the time, you do. Because I've been doing this in my open source project that some of you may have heard of called CyberDojo, that allows you to do a practice test-driven development in a browser without having to install anything for bucket loads of languages and different test frameworks, you do often get full coverage, which is no surprise. They're tests. They do one thing. There's no ifs in them. They do one thing, right? But often, this happens. These kind of things happen. So there's one, again, dead piece of code, one dead statement inside the middle function, the middle test here. And this one has nothing. What's happened here? Well, it turns out the test framework is JUnit, say, for Java. And in that particular test framework, you have to make the test functions members of the class, and you have to remember to make them public. If you don't make them public, they're not seen by the reflection. Dead easy to forget these kind of things. There's hundreds of ways you can trip up, and things are not happening the way you think they're happening. You get fooled, just like we talked about earlier. When we put the hand up, everyone fooled by a test that's passing when they thought it was failing, etc. Yeah? You might think it's very hard for this to happen. It's tremendously easy for this to happen. The system wants this to happen. As soon as it starts to happen, it's going to lock into that behavior. Yeah? I've learned something. I was really genuinely surprised how often this happens. So what happens when this happens? You see it. You put the missing public here to get the coverage back to 19 here. You look at this one. Yeah? And you think, oh, yeah, that statement is actually dead in the tests. We can delete that. Or maybe it was some refactoring that you needed a while ago, but now you've got this little helper function, yeah, that you did need a moment ago, but you don't need anymore because you deleted a line over here and you've left the function behind. Dead code. There's a carrying cost to this. It matters, right? Get rid of it. And so for me, one of the unexpected learnings was that full coverage is important, mostly so I can see when I don't have it. So as I said, for CyberDojo, I've been working on that open source project for 10 years. I started it by myself. And it's easy to maintain absolutely full coverage if you always maintain full coverage. It's easy. What's not easy is getting to full coverage if you didn't start from the beginning, because that last 0.5% are going to get harder and harder and harder because the system is not designed to be tested. Big surprise, it's not going to be testable. You can't magically expect these properties that you want in terms of the architecture of the system to exist just because you hope. As we saw in one of the earlier slides, hope is not a great strategy. You can't just sprinkle magic pixie dust on the code and suddenly it's testable. It's crazy. If you want testability in your code, you have to engineer the testability in. It's not going to happen by itself. Equal rights for tests. Tests and code. A co-evolving system, right? Unless I have a way of detecting and deleting dead code, I will accumulate dead code. We've seen it in the tests. It is happening in the code. It's harder to see in the code, unless you've done it from the beginning. It's easy to see it in the tests. Try it. Maybe you'll be as surprised as I was. So that's all I had to say. I've probably gone a little bit over half an hour. Hope I made you think. Testing and coding, equal rights for tests, a co-evolving system. Have fun, be nice to each other and to the planet. Thanks a lot.